So yeah, so this is connected to the Klein-Kordic. This is the 3-7 Coxeter diagram.
Mm-hmm.
So heptagons meeting 3 at a vertex. And so it's interesting for all sorts of reasons. But one reason it's interesting is that I was once upon a time trying to understand this famous Hurwitz automorphism theorem. It puts an upper bound on the number of symmetries that a surface can have, which is 84 times its genus minus 1. And I wrote this webpage about the proof of that. And it's a fun little number theory puzzle that basically it comes up because if you try to find 3 numbers whose reciprocals add up to just a teeny bit less than 1 and get as close as you can, then it's this 2, 3, and 7, which are really it's really a 2, 3, 7 Coxeter group.
But what are you saying? What is this, maximizing or minimizing? What is it?
So it's minimizing the difference between the sum of the reciprocals of those numbers and 1.
Oh, okay.
So it's like as flat, and what that winds up meaning is that like these angles add up to like as close to 360 degrees as possible. So it's as flat as possible. And then more analysis lets you see that that's like what you want if you're trying to make the number of symmetries of your Riemann surface be big as possible, because it lets you tile the Riemann surface with these right triangles with as many of them as possible. And if you're lucky, and it doesn't always work, but if you're lucky, there's a way you'll be able to find a way to tile the surface with genus G with triangles of this sort in such a way that you get a transitive group action on those triangles, and then you get this many symmetries. And so the Klein-Kordic is the first one where this happens, genus 3, 1. So then you get 84 times 2 is 168 symmetries. And it doesn't always work. And now I'm starting to digress, but let's see, somewhere or other.
Sure.
Like for genus 4, I think it doesn't work. And then
first of all, remind me the Klein-Kordic is genus 3, is that right?
Yeah, so 3 minus 1 is 2, and that's what's giving you the 1.
Did you say that it doesn't work for?
I think for genus 4.
What about genus 2? It applies, but it doesn't give a.
It doesn't. No, it doesn't work then. Yeah.
Okay. I mean, we thought a little bit about genus 2, right? There's some, what is it, Bring or something? Is that right?
Yeah, I think Bring's surface is the most symmetrical one of.
And it's not on the edge of this thing.
Yeah.
Okay.
So anyway, do
you want to give me at least one G other than G equals 3 where it does work? You don't have to.
Well, I think it's probably.
Where it's sharp.
Probably like I think it's probably like the next one, genus 5, but let me just, but I can't remember for sure, but it's easy enough to find out. So if I look at Hurwitz automorphism theorem, then there's a little thing in Wikipedia where they like list for a few genuses, low genus, what's the maximum symmetry. And here's the story.
7, 3 and 7, the McBeath curve.
Yeah, McBeath is the next one that hits the.
Do I ever remember reading anything about that? Not sure. 3 and 7. Well, those are mystical numbers. Is there another one? Any below that, or do it?
No, they don't list. No, and I think they know that they're. Yeah, they're only. Those are the only ones up to that point. So I guess they're sort of rare. So
okay.
Yeah, So Brings curve is genus 4.
Oh, okay,
Bolsa-
so I got mixed up. I was thinking of the Bolter curve that in genus two.
I was
Yeah, okay.
getting mixed up too.
Sorry.
It's okay. Yeah. So anyway, I was for some reason or other mentioning this stuff,
Yeah.
and Simon Pepin Lehalay said, "Oh, that's cool. These are what you're really doing is you're like getting these from child's drawings
Sure.
where." Maybe you know better than me now what he said. So
Not necessarily.
oh, well, I don't know. It's something like child's drawings that have some kind of 3 and a 7 thing going on in them. He gave some very simple sounding description of the child's drawings that would make this occur. And
Well, that's interesting. I'll have to think about that.
yeah, I mean, maybe that's all I want to say because I don't seem to be remembering it. And even if I did remember it, I didn't actually quite understand why it was true, but it was something pretty simple. So you notice one thing that's going on here is we get like PSL2's 7 and we get PSL2.
Oh, that's suggestive, whatever it
8
means.
here.
Yeah.
So yeah, so I mean, so there's like stuff we could in theory do sometime about like looking at
Sure.
those kind of symmetry groups and how they're, what are those called? Modular groups. I don't know what they're called. There's sort of reductions of the modular group.
Yeah. Yeah.
They're a very famous kind of group.
Yes. Yes.
And like how they connect up to the child's drawing story that you've been telling, like what did the child's drawings look like?
Yes.
Yeah.
I'm not sure exactly what to make yet of how the modular stuff fits into the child's drawing stuff, but it's very interesting.
Yeah. So that's all I wanted to say about that.
Okay, that's great.
The Young diagram stuff I wanted to say is far more off the track of what we've mainly been talking about.
Okay. Okay.
But it's so people will get these things called Young symmetrizers from Young diagrams.
Yeah.
And so those are elements of the group algebra of a symmetric group.
Yeah. I mean, I used to know a lot about this, and it's just not fresh in my mind at the moment. But
yeah, so
I mean, of course, I think of it in a very heck operator way. But go ahead. Yeah.
Well, that sounds good. So I mean, very roughly, what you do is you take a Young diagram, you stick the numbers 1 through n in the boxes, and then there's this thing called a row symmetrizer, where you symmetrize all over permutations that just mix up numbers in each row without moving them to another row. And then there are these things called column anti-symmetrizers, where you anti-symmetrize the numbers. You anti-symmetrize under all permutations that preserve each column. And so then the Young symmetrizer, so then it turns out that if you first do a row symmetrizer, which is an idempotent, and then you do a column anti-symmetrizer, which is also an idempotent. So the result of doing first one and then the other, it doesn't really matter which order, I think, but if you do first one and then the other, so the thing you get is not an idempotent, because the row symmetrizer and the column anti-symmetrizer don't commute. So there's no easy reason why it should be an idempotent. But then there's a thing that people seem to always prove with some slightly brute force calculation, which is that if you do the row symmetrizer and then the column anti-symmetrizer, that thing is proportional to an idempotent. So if you square it, you get some number times itself. So then you can normalize it to get an idempotent, and that's what they call the Young symmetrizer.
Yeah, there are very beautiful ways of doing this that aren't brute force at all. They're very double cosetation, very. But I can't, if I tried to explain them right now. I would get,
Uh-huh.
I would do a terrible job. But we
Okay,
should
well,
talk about that sometime.
Yeah, sometime I'd like to hear about that.
But it has a whole lot to do with Todd's philosophy of absolute colimits. Because,
Uh-huh.
when you're working in the vector space world, mostly the only thing you have to do is split idempotents.
Yeah.
And
I mean, yeah, so I know that stuff because Todd and I wrote this paper on Schur
Sure.
functors. So that philosophy is
sure, but there's very nice concrete calculus of how to make the idempotents into objects. But this is where I'll have to
yeah. So
not say anymore because I'll start screwing up if I say too much more. But yeah, there's a very nice calculus of the idempotents as objects and the morphisms between the idempotents.
Uh-huh. So what?
Can I just say something really stupid here? So
Okay.
supposing you have like supposing you have an object and an idempotent.
Mm-hmm.
Or okay, what am I trying to say? I mean, if you have an object X with an idempotent X1 with idempotent J1,
Mm-hmm.
and then you have a second object X2 with its idempotent J2,
Mm-hmm.
then you can talk about morphisms from X1 to X2, which are really, morphisms from the splitting of J1 to the splitting of J2. And there's a very simple diagrammatic calculus for that.
Uh-huh.
And that's secretly what's going on in a lot. So it's something like if you have a morphism M from X1 to X2,
Mm-hmm.
and if J1 M J2 is equal to M, then M is secretly a morphism from the splitting of J1 to the splitting of J2. And
Uh-huh.
and it goes on from there. But anyway, I'll have to work that out some other time and tell you about it more about it. But I think it's very much related to what you're talking about. But go ahead, yes.
Yeah, so these young symmetrizers are minimal idempotents in the group algebra of the symmetric group.
Yes.
And so they
irreducible, their splittings are irreducible.
Yeah.
Yeah, okay.
Yeah. And what always used to confuse me
Yeah.
is that I had sort of tended to mix them up with these other things, which are minimal central idempotents. So any minimal central idempotent.
Yeah, those are involved in the game too. Yes, very much so.
Yeah, so any minimal central idempotent breaks up as a sum of minimal idempotents. And it's like, if your minimal central idempotent projects this could work for any finite group. If it projects your group algebra down to a matrix algebra, then like an n by n matrix algebra, then there will be n minimal idempotents whose sum is that minimal central idempotent. So it's just like projecting onto a matrix algebra versus projecting onto each of like the columns in that matrix algebra.
Yes.
And I always like the minimal central idempotents better in a sense because they're canonical. I mean, so there's just like There's
Yes,
a finite
yes,
set of minimal central idempotents, and there's
yes, yes,
yeah. Whereas the minimal idempotents, they're like you can like sort of rotate them around.
yes,
Lots of
yes.
others, and so one thing that sort of always annoyed me is that you need these young, well, people seem to need these young symmetrizers, which are these less canonical things.
Yes.
So yeah. So anyway, I was just trying to well, mainly why I'm annoyed by it is because it keeps making me make stupid mistakes. But I realized there's like a way to start from a Young diagram and build a minimal central idempotent too. I mean, there has to be, but I figured out I think I figured out what it was.
Yes.
And well, so far my description of what it is isn't so beautiful. Namely, so like what I said is like you look at all these. I told you how to get these Young symmetrizers where way you think about it is like you put the numbers 1 through n in the boxes of your Young diagram, and then you first symmetrize over the rows, and you get that operator, and then you anti-symmetrize over the columns, and you get that operator.
Yes.
Yeah. So that operator that you get, the Young symmetrizer, it depends on how you put the numbers 1 through n in the boxes.
Yes.
In the first place.
Yes.
But if you average over all ways of putting the numbers in the boxes in the first place,
Yes.
then you're basically just averaging by conjugation in the group algebra.
Okay, or something. I have to think about that. But okay, go ahead. Yeah.
Conjugation action of the symmetric group on the group algebra.
Yeah.
Then that thing, because you're averaging over conjugation, that thing will be central. And well, I actually haven't checked, so it might be 0, which would be a pain, but I don't think it's 0. I think that one will be the minimal central item.
Well, okay, you haven't said out loud here that the center of the group algebra, I don't recall you saying out loud, that the center of the group algebra is something like, depending on how you do it, something like functions on the conjugacy classes or something like that. It's the class algebra or whatever it's called. Did I say it right? I always get this screwed up, but it sounds like you're very deeply entwined with.
It's functions on the conjugacy classes with this product. It's not the pointwise product of functions, but it's the convolution product. Unless I'm really confused. If it was the pointwise product, then we'd have this canonical map between the set of conjugacy classes and the set of irreps, which we don't usually get. But what we usually get is that you can look at the center of the group algebra, and you get this one basis that's the basis of the given by the characteristic functions of the conjugacy classes, and that's like a really nice basis for pointwise multiplication.
Well, maybe just, I mean, we think we just could be differing on some conventions here or something like that. What am I trying to say?
I mean, I agree that as a vector space, the center of the group algebra is the set of functions that are constant on conjugacy classes. So I'm just saying that, like, but that does not mean that we can pick out these minimal.
Right. You don't get. I'm not saying anything that means that you get a canonical
Yeah, okay.
correspondence between constant classes and irreps. But I am saying that the convolution in the center of the group algebra, convolution as an operation on the center of the group algebra, unless I'm confused or getting something backwards, upside down, I think it works out to being essentially pointwise multiplication on the space of conjugacy classes.
I don't think that can be, like, if say take an abelian group. So then one of those multiplications is pointwise multiplication, and then
Okay,
the
let me
other
think of it.
one
Let me think what you're saying. Let me
convolution.
think what you're saying. Let me think about what you're saying. All right, that's a good example to bring up. Let me think. Constant classes. All right, I'll have to go home and think about it because
Yeah.
I'm not
They're
quite
sort
getting
of
it to work out
related.
correctly. But
Yeah,
yeah, go ahead.
they're related to each other in a sort of, well, in the
Sure.
it's
I
a
mean, I know
Fourier
about that, the Fourier duality kind of
Yeah,
thing,
yeah.
but not
And in the non-abelian
non-commutative
case,
Fourier. What?
yeah, in the non-abelian case, this is why people talk about character tables all the time. Is that they're like
Sure. But
so I mean, yeah. So anyway, so what I would love would be a really easy way to get a hold of the irreps. Yeah, a good way to get the hold of the irreps of a finite group, or more realistically of the symmetric group, that did not involve this sort of non-canonical stuff about the Young symmetrizers. That just like, that is, well, I have to say it in a way that's realistic here. That would get a hold of like the minimal. I'll be happy if I can get a hold of like the minimal central idempotence in the group algebra of the symmetric group. One from each Young diagram in some beautiful way. So I figured out a way, I think, to do it, but I still don't think it's as beautiful as I would like.
can I say one thing about Young diagrams here?
Sure.
So, okay, maybe I can just grab the screen here. How do I do this?
I'll stop it, and then maybe you can start.
Okay.
Should be a green share screen thing.
Okay, so my screen is, my notebook,
Yep.
my screen is visible.
Yep.
So, yeah, this is just, again, I shouldn't really be trying to explain these things when I haven't thought about it in a while, but I'm going to take a stab at it. So let me just draw some Young diagram here, probably drawing them in some opposite convention from the way they're usually drawn. I don't know.
Actually, there's no way to tell.
All right, that's supposed to be a Young guy.
Mm-hmm.
And let's see, it looks like it's got around maybe 12 boxes in it.
Yeah, by the way, what really,
Yeah.
one thing that annoys me is that like Wikipedia makes a big deal about the English versus the French conventions for Young diagrams, but those conventions differ in whether you do it the way that you just did it, which is the English convention, apparently, or vertically reflected, which is the French convention. So like the longest rows on the bottom, but they don't seem to talk about, maybe it's good that no one talks about this, but they don't talk about like the other change of convention is to like what you're doing with the rows versus what you're doing with the columns. That is, like when you're symmetrizing with the rows, you could be symmetrizing with the columns.
Well,
That
I have no,
change of conventions is much more irksome to me, because that is not, because like I can't, you drew this diagram and I can't tell which convention of that kind you're using yet, because
well, again, I'm supposed to be trying to tell you the secret, real explanation behind all this young symmetry. I mean,
don't worry, that was just
I won't be able to do it well. I won't be able to do it well, but this is really, if you
Uh-huh.
follow this up, this is what's really going on. So what I'm trying to say is that each Young diagram represents a certain kind of double coset. And it's sort of like a double coset. It's a double coset between labeled partitions. So it's a double coset between like the row indexed partition and the column indexed partition. Those thought of as labeled partitions.
What are labeled partitions? Do the parts have names? Is that what you mean?
Yeah.
Uh-huh.
Yeah, the parts have names. Yeah.
Uh-huh.
And so, right, I mean, visibly, the Young diagram is, you can think of it that way, as a double coset between, you know, one kind of partition on a 12-element set and another kind of partition on a 12-element set. But, you know, the row kind for this diagram versus the column kind for this for this diagram. So it's a double coset. Now, you know, double cosets, like I said, they were, you know, there's this whole idea of Hecke operators, which are when you take a double coset, which is like a geometric orientation, and you turn it into a linear operator, and that's a Hecke operator, roughly, very, very roughly. I'm way oversimplifying it, but so I mean, one of the contexts where this is made into a nice slick theorem is it's probably called something like Mackey's theorem for intertwining operators between induced representations. Now, induced representations are, right, they're sort of like permutation representations, except they're like twisted by something or other. They're like twisted permutation representations, right?
Uh-huh.
Well, or at least they are, yeah.
That's
Induced
fine.
representations are sort of like twisted permutation representations, at least in this finite case. Even in the non-finite case, it's true. But so if you're working with just permutation representations, then the story is basically right that the double cosets just kind of more or less give you all of the intertwiners. But Mackey's theorem in the case of twisted permutation representations, aka induced representations, in that context, you know, the role of the double cosets is still there, but it's a little bit more involved, right? But the point is that the whole idea of Young symmetrizers is a very straightforward, very trivial application of this Mackey's theorem. That, you know, it's this double coset. You know, you use the double coset formalism of Mackey's theorem to get an intertwiner between induced representations, and the image of that double coset is kind of picking out the irrep. So that's it. I don't want to try to say more than that, but that's what to me is the morally correct way of thinking about what the Young diagram is doing to get the irrep. The Young diagram is a picture of a double coset. Mackey's theorem on intertwiners between induced representations is all about the role of double cosets in giving you intertwiners between between induced representations. And you just apply that theorem in the context of this particular double coset, and it gives you the irrep corresponding to the Young diagram.
Can you say what the induced representations are that you're applying it to? I mean, if you don't want to, that's, you can leave it at this slightly cryptic state.
Well, like I say, it's you know, the 12 bang acts on the labeled partitions that are of the horizontal flavor, and separately it acts on the labeled partitions that are of the vertical flavor for this particular Young diagram. So you get those two permutation representations, but you twist one of them by the sign representation, and you know, so you twist one of them by the signs. You don't twist the other one, and you apply Mackey's theorem in that context, and the result is that you get this intertwiner whose image or kernel or both or something like that is the desired irrep of 12 bang. So I like this because Mackey's theorem on intertwiners between induced representations is very conceptual, much more conceptual than, you know, just pulling a peculiar Young symmetrizer out of the blue sky.
Yeah.
But I just did a horrible job of explaining it. But it is correct. I just did a horrible job of explaining it.
I don't think it's horrible.
Well, I did. It came out less horrible because you asked some good questions that helped me to explain a little bit better. But yeah, I could do a better job of explaining it if I actually thought about it. But that's the basic idea. And and I'm pretty sure Todd and I have talked about this approach. But you know, between me and Todd, same ideas always end up sounding different, and different ideas always ended up, well, same ideas always sound a lot different from Todd's language compared to my language.
Okay, well, that's good. I probably won't have time.
But let me just see if I can remember.
Put it all out very
Let me
soon.
see if I can remember. I have a feeling that, you know, you didn't just randomly throw this in there, that this is probably connecting to various things we should have been thinking about or have been thinking about. I mean, it's also connected to things you've been talking to Todd about, of course.
What it's really connected to, I mean,
Yeah.
is that I'm giving these talks at Edinburgh and I'm talking about Young diagrams. So I mean, any other secret connections are sort of icing on the cake. But of course, we've always been interested in.
Well, as long as you're talking about that, let me just ask whether you've introduced it. You're planning to introduce in the discussion the fact about Young diagrams, which for me, it's the most striking fact about Young diagrams that I learned the most recently. And it's the idea that, what am I trying to say? That you can also interpret, another way to interpret a Young diagram as a picture that's telling you something pictorially, is that when you read the diagonals parallel to the main diagonal of the Young diagram, that's telling you the zeros with multiplicity of the decategorified Schur function. So like, look at this one here, okay? Sorry. Let me just draw a picture. Let me just add to the picture here, if I can remember where I put the. Damn, now I'm really big trouble here. Where did I just lose the? Oh, okay. Found it. All right, so sorry. Dropping things here, making a big mess here. I just need to add a little bit to my picture here to explain what I just was trying to say. So let me try that here. sorry, I'm making a big mess of things here. All right. Okay, so you still see my picture on the on the white screen there or whatever. Okay, so let's see. It's like you know, down the main diagonal is like 1, 2, it's length 3. And the one next to it is length, I guess, 1, 2 or something. And then the one next to that is length 2. And then one next to that is 1. And on the other side, it's 1, 2. On the other side, it's just 1. On the other side, it's 1. So you know, we're just cutting it into these diagonal slices like that and that and that and that. It's yet another way of cutting up a Young diagram, cutting up into those diagonals instead of rows or columns. And the key conceptual interpretation of the lengths of those diagonals is that those are the multiplicities of the zeros of the decategorified Schur functor. So like, why am I having so much trouble hearing you now? Did you turn down your volume? Did I screw up when I dropped my?
I think you screwed up.
Well, let me see if I can turn the volume up. Where's the volume control? All right, can you talk again?
Hi there. Hello.
I know, I realized that the sound problem happened right when I dropped my ear thing, but I still think I'm blaming it on you somehow. Yeah, because I don't think there's anything wrong here, but I just can't hear you very well. All right, anyway.
So how do you decategorify the Schur functor and get what, a polynomial in one variable? Is that what you're wanting?
Yeah. Yeah, I mean, like, you know, like this is X. This is like, what is it? I mean, you know, the vertical ones are the falling factorials, and the horizontal ones are the rising factorials, or what am I saying? You know, there's like,
okay, I guess.
I mean, this would be X times X minus 1 times X plus 1. Or like this one would be.
What happened? What about that 2-box one? You didn't just mean X, did you?
Yeah, no, right. That's just like, this should be X times X minus 1 or something. I guess it's called the falling powers or something like that.
Yep.
Yeah, and you know, the horizontal one, if I'm using the right convention or whatever, then I think this would be X times X plus 1 or something like that. And this is up to a normalization factor. I'm only trying to show you the location of the zeros, location of multiplicity of the zeros. So that doesn't depend on a normalization factor, so there might be a normalization factor of dividing by 2 here or something like that. But I'm not going to mention that because it's not really relevant when you're just mentioning where the location of the zeros is. So like I said, this one over here would be, x minus 1 times x plus 1 times x squared,
Okay, so you're applying the Schur functor to a vector space of dimension x and working out its dimension.
Yes. Are you sure you didn't somehow turn your volume down?
Yes. I can't even control my volume as perceived by you.
Well, all right. I'll have to deal with it somehow. Okay. So sorry. Again, this is another one of those things I haven't thought about in a while. But there's obviously some fascinating story connected with this way of thinking about young diagrams. All right. I guess I did get my sound to work a little bit better. So yeah. Okay. I guess we're probably done with young diagrams for now. Was
I just supposed to be able to read off that last example?
Yes.
Like, what's the story you tell that gives you like the x squared and the x minus?
Yeah, I mean, there's, 1, 2, 1. So it's, I should have written in the other order.
Okay.
X minus 1.
I see.
Yeah.
I see. So you have to believe this thing you're saying to do this computation. Yeah. Okay.
You have to believe the other story that I was telling you? Is that what you said? Or
you have to believe that this algorithm, you have to believe that stuff in red there actually works for you to crank out these polynomials that you're.
Yes, I mean, I'm just saying you count the lengths of the diagonals. You count those lengths of the diagonals and
Neat.
I mean, like I say, I just described this in a decategorified way, but obviously the fun is when you give a categorified interpretation to this phenomenon.
Yeah, that's neat. Yep. I'll
All
think
right.
about it.
All right.
Okay.
So should we try to get back to children's drawings? Should I?
Did we ever?
Yeah.
Is it? Did we ever talk about? Am I like? Maybe I'm confused. But doesn't a young diagram like give you a action of the free group on 2 elements on the guys in the boxes where like one rotates them around horizontally and one rotates them around vertically? We did that with rectangular cases, but you could do it for these other cases too, right?
I'm really not sure I caught what you said. First of all, it sounds like you're talking about something that we've talked about in the past, but is it something we talked about in the long past, or it's just like a week ago or something like that?
A while ago, we were talking about abelian child's drawings.
Oh, abelian child's.
And we were doing how you get them from rectangles.
Oh, from rectangles.
But
yes,
I was just thinking, you do get an action of the free group on 2 generators from any young diagram where one generator cycles things around horizontally and the other cycles around vertically. They don't all cycle around at the same period, but that's okay because it's a free group.
Well, that's an interesting idea. So clearly that's not going to be abelian in general. I mean, you're throwing in it sounds to me like you're throwing in a random idea there, which is related in some funny way to everything we've been talking about.
It just let
me just write that idea down. So it's sounds like you're suggesting to Yeah, what if you read a Young diagram as a child's drawing? I mean, let's think about that for a minute. Let's think about that for a minute. It's weird enough or peculiar or non-weird enough to just reminds me of so many things. Not that it reminds me of any one particular thing, it reminds me of a lot of things. Let's see. A Young diagram. Well, okay. Okay. So what am I trying to say here? See, again, I mean, we've got the idea that you can read a Young diagram as a description of a kind of permutation, but you could also read it as a description of a kind of partition. And so I mentioned how you can read a Young diagram as a double coset between partitions. And one of the things I neglected to mention is that as a double coset between partitions of two given kinds, the horizontal kind and the vertical kind, it is, if I remember correctly, it's always the most distant, the most generic possible. That might be visually obvious, right? You can tell that they're sort of, that the relationship between these two partitions is very orthogonal to each other, right? So in fact, you know, when you form a sort of Bruja hierarchy of the orientations between these two kinds of partitions, the Young diagram one will be the most distant, and that is involved in the particular way that the Mackey's theorem about the intertwiners between the induced representations, the way that works out, and the way that it succeeds in picking out just one particular irrep. So when you think, when you're picturing this as an orientation between partitions, then the Young diagram it is interesting that it represents the most distant possible, most generic possible orientation between the labeled partitions. And you're making me suspect that something similar happens with the permutations, that orientation between permutations, I mean, we already suggested, right, that there's a relationship between these orientations between permutations and these orientations between their underlying cycle partitions. So that's part of what you're doing here. But it sounds like we're saying that maybe that orientation between permutations that you're getting from a Young diagram, maybe it might be the most distant possible one, or maybe it's the least distant possible one within, but that's the most distant at the level of the cycle partitions or something like that. I don't know. I mean, I like this idea that you brought up. I'm not sure what to make of it, but there's all sorts of, it's suggestive in all sorts of peculiar ways.
Right. Now, yeah. So now, yeah, I mean, it just like was a complete random thought, but now I'm remembering that we had talked about how some aspect of the child's drawing only keeps track of the two partitions and not their orientation.
That's right.
What was the part? Oh, let's see. I may have it written down.
Yeah,
that was actually at the very end of our talk last time. So I had written down pairs of permutations gives child's drawing.
Yes.
Oh, wow. This is weird. I said pairs of Young diagrams give a census of how many 0 and 1 points have how many edges coming out of them?
That's right,
So-
pairs of Young diagrams. But one of the things you're saying is that a single Young diagram gives a pair of Young diagrams by reading it, horizontally and then flipping on its side. So that those two Young diagrams, that's one of the things that you're doing here. You're getting, you're reading a single Young diagram as a pair of Young diagrams by flipping it.
So we're getting some very special child's drawings.
Yes. It's like we're getting, it feels like we're getting something that's the most generic or the least generic or something. Again, there's all sorts of possibilities here, but I'll really have to think about it. But maybe if I just go ahead and try to say more here, but it may connect with stuff that we just said.
Yeah, sure. Go ahead and say what you're going to actually say.
Okay. So I think I still got the screen control here. Right now I'm trying to remember stuff I was going to say. And well, so one of the things that I've been working on, but didn't get as far as I wanted to, so I can't really say too much about this right now because I didn't get as far as I wanted to, was, I've really been working on getting things like Mathematica or whatever to do these calculations where I would put in the two Young diagrams. And the program would produce for me well, it would create a system of polynomials whose solutions would be the possible, well, it would be the, sorry, there's just a minor confusion here that drives me up the wall. That there's like two kinds of polynomials that are linked together here. There are these things, I think we're calling them Shabbat polynomials, which, there's this Shabbat polynomial connected to a particular nice child's drawing. And it is this, this branch cover. There are these other polynomials that are involved, which are, what am I trying to say? You write down a polynomial system of equations for the coefficients of the Shabbat polynomial. And then, you try to solve that system of polynomial equations, and and it turns out to be a zero-dimensional space of solutions. So basically a finite list of solutions. And that list of solutions will correspond to the Shabbat polynomials for all of the possible children's drawings that have the same pair of Young diagrams. So again, right, there could be all sorts of different orientations between the two Young diagrams that will give you these different possibilities. But they should all show up in this full set of solutions of possible Shabbat polynomials.
So sorry, so you're specifying two conjugacy classes of permutations, and then you're getting this polynomial equations that you solve to get the coefficients of various.
That's right. And we did talk about those last time, and I'm not really saying much more new about it, just that I'm claiming that I have been making some progress writing the program. It's been very slow progress, and I'm yeah. All I'm really saying is that I'm expecting and hoping and or expecting to learn a lot from this, from actually running my programs on medium, small children's drawings, seeing which other children's drawings they're sort of entangled with, in the sense of being in the same Grothendieck-Teichmuller orbit. I have vague plans to learn a lot about what the Grothendieck-Teichmuller action is, the Grothendieck-Teichmuller orbit is in that way. So that's about all I'm going to say about that for now. I'm hoping I'll be able to report back a lot more about that later. But right now I want to take a slightly different tack. And I want to take a slightly different tack. And this is a little bit speculative. But it's a little bit speculative, but in a way it's a natural outgrowth of the very disorganized approach I've been taking to this whole topic. So let's recall that one of my big excuses for how I got onto this topic was I still have these plans to try to explain Kronecker's Jugendtraum to you. Explain it to myself and explain it to you. And I think I've done it. I think I've made a lot more progress explaining it to myself than I have explaining it to you so far, but I've had a lot more time to explain it to myself. And I keep on getting caught into all sorts of digressions, which prevent me from trying to explain it to you. But somehow some of these digressions have sort of seemed to have circled back in some strange way, that they're now leading to me to some analogy that I wasn't quite expecting between Kronecker's Jugendtraum and Grothendieck's theory of children's drawings. And that's what I'm going to try to explain now. But it's very speculative. I don't really understand what's going on here. I mean, for me, it's very speculative. It may very well be, as usual, that somebody else already has this completely clarified. But so okay. What am I trying to say here? You go ahead. You can say something.
No, okay. I'm just saying okay.
Okay. So yeah. So like I say, I'm going to have a sort of analogy going here. So I'm going to try to draw it on my screen here with like two columns. And one column is going to be about Kronecker's Jugendtraum, which is something that I understand some things about on good days. And the other column is going to be allegedly analogous stuff relating to Grothendieck's children's drawings. Now, let me see if I can get this to work. Let me see if I can get some sort of analogy going here. I mean, again, when I started learning about the children's drawings, it was really very much intentionally trying to make analogies with this kind of stuff and with a whole bunch of other kinds of stuff, number fields and stuff, Galois theory. But somehow the analogy that I seem to be running into now seems somehow different from the analogies that I was expecting to most directly run into. It's like, I don't know, this analogy that I'm trying to explain now seems like a level slip or two away from some other analogy that I was talking about. I mean, and what do I mean by a level slip? Well, I mean, right, we talk about, there are all sorts of analogies where there are like geometric dimensions, and then there are arithmetic dimensions, and then there are mysterious analogies between these. Like when people try to claim that number fields are secretly like 3 manifolds or something like that, because it's an extra arithmetic dimension hidden in there somewhere, which something like that.
Yep.
So so let me see if I can get an analogy going here. So over on the child's drawing side, we're going to be dealing with some kind of coverings or unwrappings or something like that. And And of course, in the context of children's drawings, we know geometrically, you know, what kind of coverings we're dealing with. It's like branched coverings of the Riemann sphere. Branched only at infinity and 0 and 1. And now, what kind of coverings or unwrappings am I going to be dealing with in Kronecker's Jugendtraum? Well, it's probably not, you might be able to guess. I mean, I'm not really sure exactly what it should be. I'm not sure exactly how this analogy should go, but it's going to be really some kind of unbranched coverings of, I mean, maybe it should be, you know, an abelian variety in general or something, but I'll say of, or an abelian variety with complex multiplication in general. But let me say an unbranched coverings of some elliptic curve with complex multiplication. So roughly speaking, this is about getting an elliptic curve by taking the period lattice to be a quadratic number ring or something like that. You know, sometimes people talk about orders in a quadratic number ring or something like that. But yeah, so you've got some elliptic curve with complex multiplication. I'll just draw a little picture of the elliptic curve there. And now, what am I trying to say here? So well, there's a sort of idealized universal cover here that we could deal with, right? I mean, if you just treated this as a complex manifold or something like that, then it's got a universal cover as a complex manifold. But that's not really an algebraic, that doesn't really live in the algebraic world, but we can sort of pretend that it lives in the algebraic world. I mean, it's kind of like in, right? There's a series of other elliptic curves that cover this one.
Yeah.
And in the limit, they sort of approach a universal, in a very naive lowbrow way, they approach a universal limiting case, which is like the universal cover. So what am I trying to say? That you could sort of picture this universal cover as being, you know, something like, it's going to look like a lot like the complex numbers. Maybe I should put like the origin there, and like, you know, maybe this is 1, and maybe this is, right, maybe I'm doing the Gaussian example here, so that this graph paper really is sort of like a picture of this Gaussian integers. I mean, the square root of -1 is in there somewhere, and 1 is in there somewhere. The origin is in there. So The thing that's going to be analogous to this over on the right-hand side is going to be the sort of universal child's drawing. But let us begin to draw a little bit of. Right, again, it's an ideal limiting case. It doesn't really qualify as an official child's drawing, but it's an idealized limiting case, which you can think of as the universal child's drawing. Doing this right? Why is this? How did this come out? It doesn't seem right, does it? 1, 2, 3. Yeah, no, I didn't do the coloring right. Let me try the coloring again. It's coming out like that. Sorry. Sorry. Is coloring looking reasonably close to correct?
Yep.
So, I mean, one of the things I'm saying is both on the left-hand side and on the right-hand side, you can think of these as some sort of schemes or something. What am I trying to say? See, right, so according to the rumors we've heard, I think, according to the rumors I've heard at least, the Grothendieck Teichmuller action is like some manifestation of the absolute abelian group.
Absolute Galois group.
Yes, sorry. Absolute Galois group. That's what I meant to say. It's some manifestation of the absolute Galois group. And it can act, for example, maybe it does act on one child's drawing, you know, a particular element of this absolute Galois group acts on a particular child's drawing to take it into another child's drawing.
Mm-hmm.
But that's kind of a very high level thing. There's a way I think there's a way we can make this more concrete, more conceptually low level in a way that makes it easier to understand what's going on. So I think about this. Think about supposing you had a child's drawing that didn't move around under the action of some particular element of the absolute Galois group. So it would be fixed under that element. And in fact, this universal one would be fixed under every element. But if you think of this in a category theoretic way, you have objects and morphisms. So, right, I mean, it's like you're being a coherent fixed point. So in other words, if the child's drawing is fixed under this action, that doesn't necessarily mean that you should think of it as acting by the identity morphism. It may be that you should think of it as acting by some other automorphism.
Of the child's drawing or of the?
Of the child's drawing, yeah, of the child's drawing.
Uh-huh.
This is very disorganized in my mind, but I think it's, see what I'm saying? So like in this, right, this is the universal child's drawing. All the other child's drawings are just ways of folding or wrapping this up, okay? So in particular, if you have two ways of wrapping it up, they're in the same orbit under the Grothendieck-Teichmüller action. You know, then try and stare at this picture and try to see those ways of folding it up in this picture. I'm being very inexplicit about what I mean by that, but I think it's going to make sense. So I think we're going to see, because like, I mean, one thing people do say is that this Grothendieck-Teichmüller action will manifest as some automorphisms of the universal profinite completion of the free group on two generators. Now, I mean, you can think of the free group on two generators as manifesting in this picture, right? I mean, it's like all, right? You can identify the elements of the free group on two generators with the edges in this picture that go from a green vertex to a red vertex, from a green cusp to a red cusp. I think we've talked about that, and it makes sense that you can.
I don't know if I know that. Oh, maybe I do. Well, let's see. So like you think of the, like I'm looking at a little triangle there, and then you can think of, I don't know.
Yeah, I mean, again, you have to be a little bit careful about the two kinds of triangles. Sometimes you think of these, you know, a black triangle and a white triangle stuck together to form a so-called lozenge. If you're thinking, you know, the fundamental domain for that free group here is not the triangles; it's these lozenges consisting of two triangles stuck together. That's one of the little glitches involved in understanding this picture. Yeah, and the red-green edges are just kind of like, right? The red-green edge has two triangles on its, you know, there's one triangle on one side of the edge and one triangle on the other side of the edge. And those two triangles stuck together, those form a fundamental domain for this group action. You know, so there's this larger reflection group, but if you're just looking at the rotation group, which is the free group, then the fundamental domain is not the triangles, but the pairs of triangles stuck together at an edge that goes from red to green or green to red, or whatever.
Why does a path of the sort you mentioned correspond to an element of the free group?
It's just a little combinatorial trick. Like I say, that, you know, the rotation group is index 2 in the reflection group. So that means that the fundamental domains for the rotation group, for the index 2 subgroup, will consist of two fundamental domains for the reflection group.
Yeah, I get that, but I don't get why a path
Okay, what did you mean by,
No.
maybe I didn't understand what you meant by path.
Oh, well, what did he say? He said something corresponds to an element of the free group on two generators. Yeah, yeah.
I think I just said an edge going from a green cusp to a red cusp.
Oh, a single edge. Okay, sorry.
Yes,
I was thinking
single
of
edge.
path of edges. Okay, a edge from the green. Why is that true? I don't get
Well,
why.
again, it's just because for one of those edges, those edges are in one-to-one correspondence with these
Oh, okay, with these lozenges.
lozenges. Yes,
Okay,
yes.
okay. I was all confused because I was trying to think of the free group on two generators as like a fundamental group. So I was wanting to think of its elements as loops in something, or at least paths in the universal cover. That's why I started bringing paths into my mind here.
Ah, well, so there is something like that. It's like when you want to think of them as paths in that way, you should think of, right, there's a favorite lozenge, which is like somewhere very much in the middle.
Uh-huh.
And if you pick another lozenge, then there's a canonical path that takes you from the center lozenge to the lozenge that you're talking about. And that's this sort of path picture.
Okay.
And that path picture is kind of like tracing away through a tree, right? There's like a tree structure here.
Uh-huh.
Being very sloppy here, but yeah, but
Yeah,
that's how it
no,
works.
I know that tree. Yeah.
So I guess you're right. Maybe that is just the Stern-Broco tree, but it's probably also has other. I shouldn't really say it's the Stern-Broco tree. It's related to the Stern-Broco tree, but it's some very famous tree related to the free group on two generators. But so what I'm very sloppily claiming here is that we should be able to interpret the action of the absolute Galois group on the child's drawings in general. We should be able to interpret it as really just an action of the absolute Galois group on this one single universal child's drawing. In a way that involves thinking of all the children's drawings, all the non-universal children's drawings as being little aspects of this universal one. And they're not exactly parts of it, but they're sort of like co-parts of this drawing. So that's what I'm sort of suggesting, that we should be able to interpret the absolute Galois group as just acting on this picture in a certain way. Now,
so the absolute Galois group in this dream is supposed to be some subgroup of the, maybe like the, I don't know why I'm saying this, but of the profinite completion of the free group on two generators, or some.
You may have left out a level step there or something like that. That it's a subgroup of the automorphism group of the universal profinite completion here. Again, according to this, I'm saying this, I'm repeating rumors here basically at this point, but it makes sense in a bunch of ways.
Can I think of it as a subgroup of the automorphism group of this picture?
It's slightly delicate. If you sort of think of the sort of idealized, you have to, it's subtle. It's subtle because the universal profinite completion is bigger. It's a completion than the original thing, and the automorphism group is also bigger.
I mean, it would be annoying if like the Galois group,
Say it again?
it would be annoying if the absolute Galois group only sort of lived in that bigger stuff. Like it might not have any elements.
No, it will have some elements. It will have some, and in some sense, you should be able to, you shouldn't really need to use your, infinite vision to see it. You should be able to sort of see the absolute Galois group in some sense level by level. So if you sort of put a cutoff at a certain point, you should be able to see the corresponding cutoff version of the group. But like I say, it's subtle. I'm not sure I know exactly how to work those cutoffs in such a way as to get it to work exactly. But I think it does work. And I'm also right now I'm getting very paranoid about whether I'm going to have equally bad problems over on the left-hand side over here. So what I want to say over on the left-hand side is that we're going to have Kronecker's Jugendtraum telling us that something very analogous is going on here. So what am I trying to say? That over on the left-hand side, we have this very additive picture, right? The period lattice is sort of an additive group. Well, I have a feeling, right? I have a feeling we should be taking some universal profinite completion of this additive group as well. Well, also, I mean, what am I trying to say? Like, I mean, I'm wondering if if a certain group of people is going to say stuff like that these aren't really algebraic varieties, but they are pro-algebraic varieties or something like that. I'm not sure that's the right way to talk, but I can, right? I mean, like,
I already wrote that word down. Yeah, I think some people say that stuff.
Pro-algebraic variety? Again, I'm not sure that's quite the right idea, but I can imagine somebody saying it, and it's going on both on the left-hand side and on the right-hand side. This, and that's sort of, so right from the geometric picture, it's sort of it's giving us pro-algebraic varieties, but from the algebraic picture, which is sort of dual, it's really just giving us these coordinate algebras, or perhaps homogeneous coordinate algebras that are really big, have lots of generators. They're not finitely presented or something like that. But anyway, what am I trying to say? That in the picture on the left-hand side, we have the period lattice, which is an additive group. And then we have like multiplicative symmetries of this additive group. Or perhaps I should say we have multiplicative symmetries of the finite quotients of this additive subgroup. Right? I mean, so like, right, we have this.
Hold on just a second. I need to check something, sorry.
Okay.
Okay, it's okay.
So I'm trying to set up this analogy that I'm trying to set up between the left-hand side and the right-hand side. On both sides of the screen, we have something and something that acts as an automorphism group of it. So on the left-hand side of the screen, we have the sort of like the additive group, and its symmetry group is some sort of multiplicative group or something like that. And it's like, it's like the it's like you've got this quadratic number ring. And it's got an additive aspect and the multiplicative aspect. And the multiplicative aspect is like symmetries of the additive aspect.
Uh-huh.
Whereas over on the right side of the screen, what we have is the picture. The picture is a picture of the universal profinite complete. Well, the picture is a picture of the free group on two generators in some sense. Only we're supposed to somehow think of it, think about the universal profinite completion instead. And then it's got that group has some symmetries, and that's some, and so the action of the absolute Galois group is going to be some manifest. It's going to manifest as some symmetries of this picture, or symmetries of this picture, or symmetries of the profinite universal profinite completion version of this picture. So
what's the group over on the left-hand side? Sorry,
the group over
the thing that's like.
Well, so one of the things that you can see that's going on is that in some sense over on the left-hand side, everything is abelian. So it's actually going to be the abelian absolute, the absolute abelian Galois group. And that's what the Kronecker's Jugendtraum is sort of all about. It gives you a very concrete picture. It is doing something very analogous to what the children's drawing is doing, but it's doing it in this very abelian, limited abelian context. And well, actually, I'm getting a little bit confused here because I'm not 100% sure whether I should really be saying absolute abelian or whether I should be saying relative abelian. So what am I trying to say? That, I mean, you could have the absolute abelian Galois group of the quadratic number field. And that is what? That is contained in the absolute Galois group, but it's not contained in like the center or something like that. I mean, am I saying this right? What am I trying to say? Am I getting subgroups and quotient groups mixed up here? I mean, right, one thing you can do is you can take the absolute Galois group and you can abelianize it. And that's like the absolute abelian Galois group. But another thing you could do is you could take, don't start from the ground, start, relativize a little bit, start from a quadratic number field and take its, the sort of relative absolute Galois group and abelianize that.
I mean, here we're on the left, we're baking in a particular quadratic number field.
Yes.
Start. Whereas at right, we're not doing anything quite analogous to that.
That's right. I mean,
we could try to do something more dramatic at the left, but that's okay.
Yeah, I mean, right. I mean, so one thing that's going on here is I'm struggling to make an analogy here, but I should also say that I'm not even sure whether this, for all I know, this could work out to be better than an analogy. It could be that these, it could be the thing on the left is actually in some sense a special case, not exactly of the thing on the right, but I mean, there's this whole general Grothendieck Teichmuller game, which is more general than just children's drawings. And if you conceive it generally enough, then I'm not even sure that the Kronecker's Jugendtraum thing on the left, I'm not even sure that doesn't become a special case of this Grothendieck type more stuff.
That would be cool. I mean, looks like the thing on the left is about like the genus 0 curves, and the thing on the right is about all higher genus curves or something like that.
No, it's more like, you sure you didn't mean genus 1? I mean, the thing on the left has a whole lot to do with genus 1.
I meant genus 1. Sorry, I was thinking Euler characteristics here. Yeah. Okay. Well, I don't know what I meant. I don't know. Something like, I guess I was thinking like how the one thing on the left seems to be like flat, and the thing on the right seems to be hyperbolic.
Well, that may be that there may be something to that. I was thinking of it more naively, that the thing on the left is sort of abelian and the thing on the right is non-abelian. But maybe that might be secretly the same as, or almost the same as what you're talking about.
Yeah. Okay. Well, anyway. I don't know.
So.
Yeah.
I mean, what? Yeah.
Did you ever flesh out something specific on the left that was, and that's supposed to be analogous to how the absolute Galois group is acting on the profinite completion of F2 on the right, or you just sort of, you seem to be sort of trying to make up your mind what's a.
Well, I'm struggling here, but I mean, there is something in the Jugendtraum, right, where the Jugendtraum is all about this idea that the absolute abelian Galois group, and again, it could be that when I say about absolute abelian Galois group, I actually mean relative abelian Galois group or something here, or relative absolute abelian Galois group. But what it is you get the you get some absolute or relatively absolute abelian Galois group to act on the torsion points on the elliptic curve. And they act in a way that's very connected with the multiplicative structure of the quadratic number. I mean, it is just kind of the action by the multiplicative groups of the quotient rings.
Another multiplicative groups. One thing I'm confused about is how.
Yeah.
You mean multiplicative groups of number of rings, or multiplicative groups of number of fields, or do you mean like multiplicative monoids of number?
It's multiplicative groups of quotients of the number ring.
What kind of quotients? Sorry.
All the quotients of the number ring, like the quotients of the Gaussian integers. So each quotient of the Gaussian integers has its own little multiplicative group. And all those multiplicative groups sort of fit together. You sort of take something like an inverse limit of those multiplicative groups or something like that.
And what is that? I don't know if I've ever thought about that. I should have. So you're like taking a Gaussian integers and reducing mod p or something like that for prime, or does it even need to be and then you're like looking at the.
Yes, it's like a Gaussian prime.
Yeah, I feel like I should have understood this when you're talking about things like art and reciprocity, but that I didn't. I don't quite.
Right, partially because I never kept on that same track for very long. See, I admit I really think something should work here, but I admit there's a whole bunch of things I'm getting confused about. Like, I'm trying to get these torsion points to appear very naturally in the picture, but there's something fun. I mean, as you unwrap the elliptic curve more and more, and in the limit, you sort of get a flat plane, which looks a lot like the complex numbers modulo, the complex numbers with this period lattice in it, which is the quadratic number ring.
Uh-huh.
It's like, it's less like you're subdividing to get the torsion points than like you're going out in the opposite direction. You're making things larger, but maybe somehow that's equivalent. Let's see.
Well, I guess there are torsion points in covers.
Yeah, but I'm trying to get this, I'm trying to get the action to cohere as you unwrap, and I'm not sure I'm doing it right. Let's see. See, if I can get this to work, if I can get this to work, then it would be very nice in a lot of ways. But it would also, I mean, one thing it would do is sort of help to explain how the Jugendtraum works. Let's see.
Mhm. I would just say another stupid thing while you,
Yeah, go ahead.
while you're thinking, which
Yeah.
is that, like, from another, this is like different than some other thing I said. So
Yeah.
from some other point of view, the right-hand column is about genus 0 stuff. Maybe you said it. And the left-hand column is about genus 1 stuff, because you're taking branch covers of, well, I don't know, it's weird. You're doing branch covers of genus 0 stuff, unbranched covers of genus 1 stuff.
Yes.
And so that makes me wonder, like, okay, what about higher genus stuff?
Well,
Maybe-
I think that higher genus stuff is going to fit together in the same picture, more on the right hand side than on the left hand side.
Yeah, I guess because those branch covers get to have higher genus themselves. So
Yeah.
sort of do another stupid thing. Like, did we ever talk about? I guess we did, but did we ever talk about branch covers of CP1 that were elliptic curves? I guess we did, but
We talked about them a little tiny bit. I mean, for example, we had a billion examples like that.
So the abelian child's drawings are giving us those? Is that what that was?
Only some very special cases. You could get, we were able to get like
Okay.
the Gaussian elliptic curve and the Eisensteinian elliptic curve. Those are both very simple examples of abelian child's drawings.
Okay.
But
Yeah.
presumably those also occur as non-abelian child's drawings. I would imagine.
Yeah. Yeah. Okay. Anyway, this is very appealing, but yeah.
It's very, but I mean, I knew it was very unclear, but I didn't realize it was this unclear. Let's see. Well, I mean, maybe I should just go home and think about this more. I mean, this is really helping, but so far this is very speculative. I mean, I'm hoping that this won't be speculative. I'm hoping this will be better than just speculation. I'm hoping this will be, but boy, I really need to think about this some more.
One other stupid thing I was going to say is that the covering map from the universal cover of the elliptic curve.
Yes.
The elliptic curve. So that's this elliptic, that's an elliptic function.
Yeah, you can think of it that way. Yeah.
And so that's I'm just sort of saying something that you've mentioned before. So that's sort of weird because that's like a transcendental function. And we thought we were doing algebra.
Yes, yes.
But then I never quite thought about it this way. But then the finite covers of the elliptic curve,
Yes.
those are all algebraic, right? Those, I mean, those, yeah.
Right,
Those
right.
defined.
Right.
So there's some weird sense that I never thought about before, where you can think of like.
I mean, and a lot of them are just the cover itself, just rescaled. The original elliptic curve itself, just rescaled.
Yeah.
But keep on going with what you were saying. Yeah.
Yeah. So this is, I just never quite thought about this way. You can think of the elliptic function as some kind of limit, in a very categorical sense of limit of these algebraic functions between elliptic curves.
Yes.
So that's, and then over on the right, so there's so for any,
I mean, and over, I mean, there's things that are a lot like sort of the whole algebra of modular forms. I mean, this is even more general than that. Right, one of the things people sometimes,
yeah.
right, if you put a level cutoff on the modular forms, then you get this, you know, algebraic stack or something like that. But if you don't put the level cutoff, then you're getting this sort of pro-algebraic stack or something like that.
Well, okay.
Well, I thought that's what you were getting at, but
well, I was somehow the word stack threw me. I was just thinking there must be like some transcendental functions, which are modular forms that describe the branch covers mapping hyperbolic plane down to the sort of finite level branch covers. But then they're also, I guess, sort of like, I think that there must be like purely algebraic maps from some branch cover down to some other branch cover. I'm imagining this big tower of branch covers and branch covers.
Yes.
So the sort of finite level branch covering maps should be algebraic, I'm thinking.
Yes.
But then there's this same situation that there's this limiting case version that's like a transcendental function.
Yes.
So I never heard of anyone talk about transcendental functions as limits of algebraic functions in that.
Well, it's a strange idea, but yeah, go ahead. Yeah,
it's a strange, it's an interest. It's so funny. I mean, when you say limit of functions, an analyst always thinks you mean some other kind of limit. This is like a inverse limit kind of thing. So anyway, that's interesting.
Yeah. All right. So I'm going to go home and think about this stuff.
Okay.
I hope I can explain these ideas much more clearly as we keep on talking. But I'm going to go home and think about it for now.
Okay. Sounds good.
Okay. Thanks a lot. I'll see you.
Yep. See ya.
Okay. Bye.